In order to turn liquid water into solid water, it is necessary to lower the temperature of the system. And obviously, if we go below 0 degrees, water, under normal conditions, will turn from an ordinary liquid into ice and change its state of matter. But then why can we find such a state on the phase equilibrium diagram where, under normal conditions, water is a solid? That's what we will talk about today. My name, as before, is Yuri Trifonov, and today we are figuring out whether it is possible to turn water into ice by simple compression. I anticipate many questions. I'll start by saying that liquids are also compressible. Very often you can encounter the common belief that liquid cannot be compressed at all, and that liquid is indeed incompressible. This belief stems from the fact that in many manuals, for example, for hydraulic brakes or other hydraulic systems, it is noted that liquid is incompressible. But if you study the issue more thoroughly, you will find out that liquid is not incompressible, but rather liquid is practically incompressible. And this small addition fundamentally changes the perception of the system. And yes, it turns out that at high pressures, liquid is absolutely compressible. Let's recall how water, or any liquid, preferably water because it's easier to work with, transitions from its normal state, from a liquid state to a solid state. It is all very interesting, all tied to one fundamental and basic phenomenon. This is the internal energy of the particles, the internal energy of the system. As long as the particles of the system, in this case the water molecules, have the ability to move actively. These water molecules cannot form solid frameworks, if we can call it that. As long as the particles that make up the framework of this material have energy, they cannot be in a stable and stationary state. Yes, even solid material, B, has its own characteristics, the specifics of the pulsation of these structural components. Or in other words, even in a metal rod in its solid state, as long as it is not melted, the atoms of this metal will move and pulsate around their equilibrium points. If we look at the liquid state, it differs from the solid state only in that the characteristic lattice we talked about is destroyed. Everything mixes, but the bond between the particles of the atom molecules is preserved. However, despite all this, they gain more freedom. This means that the elements no longer just pulsate, but move within the volume quite freely. The absence of a strong bond between the elements of the system allows for the liquid aggregate state. Well, what is the measure of the amount of energy in the elements of a system? Yes, my friends, it is temperature. And in the case when we talk about the liquid state of matter, the temperature is usually higher than that of the solid state of the same material. This is a basic truth that we know from life practice, and which follows from the school physics course. We all remember this very well, but for some reason it is usually very well remembered. So it turns out that as long as the elements of the system have some energy, they can actively move. Their thermal motion is intense, and there is no possibility to organize a dense framework, a strong structure, which we have already talked about, and which resembles that very framework of metal, or the framework of ice, but it is a bit more complex. Therefore, yes, we said that we are talking about the structure of metal specifically. Accordingly, a decrease in temperature implies a loss of thermal energy by the system and a loss of this energy by the elements of the system. This means that the elements that make up the system, which are the building blocks for this system, start to move less intensely. When water is cooled, its molecules begin to move less intensely, and some ordering in its structure is formed. This ordering, in essence, is the formation of ice crystals. The same happens in metals, and everywhere and everywhere and everywhere. And essentially, the rational way to extract thermal energy is cooling. But let's return to the phase diagrams, which everyone dislikes so much. If you look at the phase diagram, where the state of water is marked relative to pressure and temperature, you will see that even at room temperature, under certain conditions, water can be solid. Well, here we need to remember that there is such a thing as thermodynamic parameters. There, we have pressure, volume, and temperature involved. This means that all the parameters are interconnected, and this also means that all the cases we analyze regarding the aggregate states of material behavior can be correlated with the fact that when one of the parameters changes, the state of the entire system changes. This implies that even without altering the temperature, we can change the state of the system simply by changing the pressure. In fact, this is exactly what we see on the phase diagram, where we have ice, water ice, the most common ice we can find, but at high temperatures. This ice will not be cold, but it will be solid. How is this even possible? If we analyze the behavior of the system and the behavior of the elements, we understand that this movement of particles, limited by their thermal energy, becomes slower because the energy is being dissipated outward. But there is a simpler way. You can simply not allow the particles to move. So how can we prevent the particles from moving? It's very simple. Confine them in a compressed volume. This is the very toy, the neocube, that I constantly recall when I talk about this. So if we imagine that the elements of the neocube not only attract but also repel each other, at some point they will hover in the air at a certain distance, which will provide exactly the phenomenon of both attraction and repulsion while maintaining the system's cohesion. As long as the system is bound by as a single whole, we find that the structure exists. And so essentially, this attracted neocube is equivalent to what we have with the crystalline structure in a solid state. While they are piled up in a bucket, we can shake, shuffle, pour, and do whatever we want with them. It somewhat resembles the aggregate liquid state, or the state of water at normal temperature. But if we take these balls and start pressing on them with some kind of piston, or simply push the bucket with our hand, or press with our foot, the distance between the balls themselves will inevitably begin to decrease. The balls will move relative to each other, and thus eventually form the densest packing. Now let's combine the two examples about the balls in the bucket and the neocube. The liquid state, illustrated by the balls poured into a bucket but not rigidly connected to each other, will gradually begin to be replaced by a solid aggregate state, where the balls are not just poured into the bucket, but have arranged themselves in a specific orderly manner, occupying the closest possible positions. And also, recalling the neocube, where the balls interact, they began to attract each other more strongly. All of this will lead to the fact that the change in pressure formed stronger bonds. So my friends, the same thing can happen with water and pressure. And now let's return to the diagram and see that the pressure we're talking about is actually not 2 atmospheres, not 3 atmospheres, but some incredible values. What we just discussed. Or simply take the elements of this water structure, move them closer together, and forcibly form a bond. In essence, we form an aggregate state without changing the typical energy. And we no longer care that the particles are actively moving and so on. As long as we start compressing these particles in a certain enclosed volume, their own thermal energy leads to nothing. We just need to use high external pressure to make the particles move relative to each other, occupy the position they should in a solid aggregate state, and thus form the framework of this system.